Great. So it's fantastic to be here. This is one of these, I'm going to talk about meetings a little bit. So this is one of these meetings that's fantastic because we're all sequestered away and there's lots of time for discussion, which hopefully we'll all have later. So actually, yes, I'll start with this book. And I start with it because, you know, here we have all these people who have funded and, you know, we all fund science, right? You fund for it because you pay your taxes in society and you buy products and you give money to charities, which is generally the way that all our science is funded. And we all go to conferences. So this book is actually written about how science really works. So we're all embedded in science in different ways, but I challenge you to tell me how many scientists there are in the world, or how many physicists, how many people you're competing with. Is it going up or is it going down? So those numbers, we actually understand some of those things. Also the competition, how competition works, and why you tell me there are, you know, you're going to too many conferences. Well, don't. But of course the pressure is to keep on going. So there are all sorts of strange things about the science world that we live in, and that's why I wrote the book. But one of the things we have very little information on is about actually conferences. You know, apocryphally, all people will tell you, yes, there's more conferences than there used to be. But there's zero data on that, actually. And as we go up in the profession, right, you go up your career path, of course you go to more conferences anyway. So is it just the old people just, you know, complaining? Right? How do we really know? So actually one of the things I'm trying to collect is data. So there's this website here, thesciencemonster.com, where actually there's a survey set up. Well, I'd be really interested if you actually all would just fill out that survey. And I'm just trying to get more of a picture. I've sent it around all sorts of communities, chemists, physiologists, so we can see some of the differences that exist in fields. And why do we go to conferences? What's the best conference? Why do we actually let bad conferences carry on existing? Why don't we kill them? Yeah? So that's all about this. So I'm going to talk about extreme optics, nano-optics, and I hope by the end you'll agree that I'm allowed to even use those words, extreme nano-optics. So I'll mention some people at the start because I probably won't have time at the end. So there's a whole set of people that you'll find have contributed to this work. I'm going to pick out Barjanese and Giuliano Di Martino and now Rohit Chikkarati, who are postdocs who've been really pushing this work forward. I'll show some stuff from Felix Benz before and some stuff from Maria Elena. But there's a whole range of people as well. Yes, and Femi Ojumbati. I'm sure going to show you some new data as well. And then this work has to be collaborative. You'll see it's very collaborative on the chemistry side. So Oren Sherman's group in Cambridge and also Ulrich Kaiser's group is the work that I'm going to show you on the DNA origami. And that's been done by Vlad Turek and now a couple of students as well. And then on the theory side, there's a whole range of people as well. I've worked with Javier Thuri's group in San Sebastian for a long time. Angelin Dimitrudou was a postdoc going backwards and forwards between that group and Ortwin Heste's group in Imperial. And Nicolás Schmidt has done a lot of the optomechanics I'm going to show you as well. So whole set of people. So the place I like to start in this talk really is, I call myself a nanophotonics person. And for many years we did photonic crystals and things like that, but actually it's not very nano. I mean, you're still talking hundreds of nanometers typically for anything that's structured like a photonic crystal. So we're not really looking at light on the nanoscale. So one of the things that's driven my work over the last 5 or 10 years is just how far can you go in confining light? So I worked on early SNOM actually in the late 90s when it was just coming out, and that taught me never ever to try and do that again. Sadly, I'm finally just going back into SNOM slightly, but difficult techniques to get something new out of. So all of these ways of confining light, these are dielectric cavities, for instance, whispering gallery modes where the light bounces around by total internal reflection, or photonic crystals where you have light that cannot propagate in these holy areas here, where these are about 100, 200 nanometers across, and there's slight changes in the spacings here, which mean there's a mode trapped there, or a micropillar like this with a gap where the light is resonating. But all of these basically have the optical mode volume about the wavelength of light in the material cubed. So on the scale of nanoscience, that's pretty terrible. So that's millions of nanometers cubed. So we want to really do better than that. And so why do you want to do better? Well, one of the ways to think about it is the interaction with electrons. So if you're looking at interaction with the individual objects, the interaction, this sort of light-matter coupling, goes as something like 1 over the square root of the volume of the optical mode. And if you like, it's how long it takes that photon to go around the cavity and come back to where it started with. The bigger the cavity, the longer the time, therefore the less the interaction strength is. And with vibrations, it goes as something like 1 over v, and you'll see that's what's sort of interesting. So we want to do better by really looking on the nanoscale, and also, of course, we can get intense fields, so non-linear effects also become important. And for me, there was also sensing, and I'll talk a little bit about sensing. So I'll talk about how we confine light at the start, and I'll try and give you a view. I mean, actually, the theory is really good to understand in this area, to see how you might be able to go forward. I'll talk quite a lot about molecular systems, and then I'll talk about the ultimate confinement, where you can confine light down to the size of an atom and less, which we didn't believe we could do a few years ago. So I think you all know this area here. So basically, this is the coupling between plasmons. We know plasmons on individual nanoparticles are set. You send light in, and it sets the electrons, the free electrons in the metal moving, and you get something that looks like a dipole response. You can get higher order responses, and you can see the field lines are concentrated at the poles here. So you have a field confinement, which is on the order of 10 to 100 nanometers. So it's still not that large, and I always say it's the only thing that plasmonics has been good for until now, because that's how stained glass works. But it gets really interesting when you have two pieces of metal where the electrons can oscillate, because then the local field produced by these electrons moving, it acts on these ones. So these ones see not just the external field, but the local field from these ones. They respond in a certain way, which acts back on these ones. So it's a dipole-dipole sort of interaction, a bit like two bar magnets, which you can feel the forces, very strong distance dependence on your bar magnets. So the same thing, except that these are induced dipoles. So the interaction is more complicated because they're not fixed, they're actually induced by the light and the interactions. What happens in the end is that as you bring these two together, the mode, instead of being around the whole nanoparticle, gets trapped into the gap. And there's a resonant frequency which goes to lower frequency, so it shifts off into the infrared here. And it's a ferociously sensitive to the gap size here. So you can see for typical 50 nanometer nanoparticles, everything is interesting in the last few nanometers. So this mode goes off into the infrared, it carries on going forever in the last little bit, and also the light here gets enhanced by 10-fold or 100-fold or 1,000-fold. So this is the domain that we want to be in. So we started trying to make gaps of the order of a nanometer, and for that, it's so sensitive you need to be able to control that to 0.1 nanometers, so less than the atomic scale. So that's the real challenge to be able to do. So a number of years ago we tried it in a sort of heroic experiment that I'm not really very keen on. So this is two gold nanoparticles attached to AFM tips, which are brought tip to tip within a nanometer and then controlled. And so what you do then is you look at the light that's scattering in that gap there, just like that. And you can see a particular mode, and it looks basically like that, except that as you get very, very close, this has to break down. I mean, there's no way it can just carry on going to infinity. It's a sort of ultraviolet catastrophe. It's one of those cusps. So what happens is that it breaks down, and the reason it breaks down is that you're building up charge within an optical cycle either side of this gap here. It's essentially just a capacitor working at optical frequencies. So the electrons on this side here, during a half cycle, can actually quantum mechanically tunnel through that gap. And when they do that, they discharge the capacitor, so it no longer redshifts as much. So the redshifting is basically telling you you're building up charge on either side of that gap. So you see some changes here, which are just from the quantum tunneling. And that all works at room temperature. And there's a typical size scale there, which is about 0.4 nanometers, which is pretty hard to change. So there's not many ways to control that very easily. So at the time we thought the minimum volume you could confine light was basically given by the size of the nanoparticle times this size squared. So it's small but not absolutely small. So that's on the order of about 50 nanometers cubed. So that's what I'm going to show you at the start. So you still can do zectoliter chemistry. But I'll show at the end we can do better than that, and in fact we can still, that formula is still correct, but we just made a mistake. It's always good to make a mistake. So the problem about making these gaps is that it's really, really difficult to do. So it's one of these areas. I used to work for IBM and Hitachi, and I was using lithography. This is a disaster to use lithography for, because if you try and say make a 3 nanometer gap, this is the best from a Singapore group, you make a 3 nanometer gap, you do it 1,000 times, you'll get everything from 10 nanometers to -5 nanometers. Even though people will tell you their resolution is 1 nanometer, is a fantastically expensive EB machine that they're using. When you're trying to make metallic structures on the top of that, there are lots of things that go on that mean that you can't control the morphology there. Break junctions were interesting 20 years ago. They're very hard to use for this because there's lots of light scattering around, but they should work. And recently there's been more interest in using those. So you make a junction where you break it, and when you've just broken it, you can control the gap a bit. Then there are ways that you can put large fields on an STM. It's very hard to get light in and out, and it's not an easily accessible technique, STM. But again, there's lots of work now in this area. But even molecularly, it's not easy to get this control. If you just put colloidal molecules around particles, it's very hard to control the gap size to 0.1 nanometers. Or DNA, which people tell you is rigid, on these size scales, it's not rigid. So you have to do something more than that. So the first thing that we did a number of years ago was we used this molecule here, which is a bit like a cyclodextrin that we have in our bodies. It's a very familiar sort of molecule. This is a very nice version of it. It's called, it's a cucubitrol, which just means pumpkin molecule. So it looks like a pumpkin. It's been known for 100 years. It was an oddity. It's a very strange synthetic route. You cyclize glycuryls. This is a carbonyl bond at the end here. That's an oxygen. There's a carbon underneath it. So there's a double bond there. That turns out to stick to gold really well because it's negative on the oxygen, which induces a positive charge on the gold. So it's essentially an electrostatic attraction about half the size of a thiol bond, so a very strong bond. And it's got a hole in the middle of it. And you can make it of different diameters, but it's always got the same length here, which is 0.9 nanometers. So what you can do is use it to stick together metallic particles very robustly. You can put things inside it. What goes in is something that's slightly hydrophobic, but it doesn't pick out unique things. Many small molecules can go inside, and you can start to select them. So it's a rather nice system for various reasons. So now we know, so what we know is that when we make a small gap like that, we have a very strong enhanced field. So anything that depends non-linearly on the field is going to be enormously enhanced. So things like third harmonic generation, all those sort of things are enhanced, but also Raman scattering, which scales as the optical field to the power 4. And that's because in Raman scattering, you send in a photon, and there's some probability, mostly the photons just come back out the same color, but there's some small probability of exciting a vibrational mode of whatever's in the gap, in that field, and so you absorb a little bit of that energy into the vibration, so you get a red-shifted color coming back out. And normally it's a very weak process. 1 in 10 to the 10, 10 to the 12 photons will do it. So the nice thing here is that this scales as e to the 4 because you've got an e squared going in and an e squared coming out. That's why it's e to the 4. So if you've got a 1,000-fold enhancement in field, you get a 10 to the 12 enhancement in that Raman signal, and that's what's going to let us get down to the single molecule level. So the nice thing is that we can now combine these. This is an experiment a professor can do, because you just take some gold nanoparticles and CB molecules and you mix them together, and they have this interesting sort of aggregation. They make long spindly aggregates when they bounce. You can actually just take Velcro on tennis balls and throw them at each other, and you get these random fractal aggregates. They're quite one-dimensional actually. So the optics here is a one-dimensional chain of plasmons which are all the same color because they're the same gap size trapped here, which all mix together. So there's some very interesting optics here, and people can come and talk to me about it if they want to. But you have to control the gap sizes precisely to get it to work. So then you very efficiently couple light in, you very efficiently scatter it, and you very efficiently get the light out. So we can actually just look at the Raman spectrum, and Raman spectra are measured in change in energy from the laser. So the laser's at 0, and these modes here are vibrations which are at different energies. So in a slightly strange unit. So that's about 40 millielectron volts, for instance. So these are modes of this particular molecule which can flex in different ways. Now I can put something inside it, and I can see that very directly. And in fact, I can put 2 molecules inside. One will pull in the other, and so I can see these bonds. It's a fingerprinting technique which is tagless. You don't have to add something which emits light onto it. I can just look at the molecules which are stuck inside these cavities. So we've been playing with that in various ways. So one thing you can see here is when the molecule goes in, if it's a big molecule, it stretches that. So if I look at this mode here, as I put bigger molecules inside, you'll see that this mode splits and goes in different directions. And that's because I'm splitting the modes around the equator here, because I'm stretching the whole thing. It's really important because I can actually be quantitative then. I can look at these and I can say how many are filled. And then if I'm trying to do a biochemical assay, I can actually say how much of that chemical is around. So one thing that we've been doing is actually developing this for the intelligent toilet. So we're actually trying to deploy this in the home because we found that we can look at urine and we can look at neurotransmitters at clinical levels in urine. So they're there at below micromolar concentrations. And they're small molecules, dopamine for instance, serotonin, and they go inside the CB and we can see them at these levels and we can actually get quantitative information. So this is a whole big area, and I'm not going to talk about it anymore, but it's enabled completely by the physics behind it, the optics. So now let's go back to the physics side. So what I really want to do, of course, is I want to get the best possible confinement. So I want to make the thinnest sort of gap. So I don't want to have to use 2 AFM tips because that's complete pain. So I'd like to put something in there. So the thinnest thing we have is graphene. So it's 1 atom thick. So the problem is that you can't get graphene to do that. Gold, once you put one gold nanoparticle on, the other one will not go anywhere near it. So you have to think of something else, and then that's why we really pushed onto this idea of the nanoparticle on mirror. So the thing about this is that it's hard to make, but if I just put this gold nanoparticle with a thin gap on a metal plane, we can use some of the ideas from undergraduate, these ideas of image charges, to show it's the same thing. So you know that if I have a charge above a ground plane, I can actually replace the ground plane with an image charge the same distance below, but opposite, so plus to minus. If I've got 2 charges, I've got a dipole, and I get an image dipole below it. If I've got a nanoparticle with all sorts of things going on, I just have an image nanoparticle, and the interactions are essentially the same. In fact, the only difference is actually this nanoparticle on mirror has a slightly stronger interaction than the dimer, because essentially there's more metal at the surface there, so there's more electrons that can move around. But the physics is the same, and that is easy to make. So, for instance, we can take a gold sheet, we can put down different numbers of graphene layers, put gold nanoparticles on the top, and one of the ways that we'll look at this is we'll actually shine light in at some angle, which will excite this resonance. The light is stuck in a gap there, and it will scatter light, the resonant light, in all directions. So if you just look at the color in dark field scattering, the color of each one of these is 1 nanoparticle, which is sitting on there, and they have different colors. So you can just take the spectra of each one. So for instance, if you look at the spectrum when I have 5 layers of graphene, I see a mode that's shifted to the red. That's what I expect because it's a small gap. This is the coupled mode here. This is a transverse mode. So, and as I make it thinner, so this is 1 layer, it shifts to the red. So it's just what I showed you at the start. So this is sort of the ultimate, but you can see there's other stuff going on here. There's splittings. So we had a model for that, what was going on, but I'll show you more about how that's sort of working. So you can also do this with these cucubitrils, these pumpkin molecules, the CBs, and works in just the same way. And I can actually do this, we now have automated setups where I can measure the scattering on thousands of individual constructs, say in a night, we just let it go. And each one of these is a dark field spectrum. And if I look at those spectra, they're all the same, essentially. And if I look at those modes there, essentially the differences come from the fact that the gold nanoparticles are not all spherical. They're all slightly different. And I've taken out maybe 1/3 of these, which are actually coming from flat little triangular sheets. So prisms, nanoprisms, which give a very different spectral signature. So it's very hard to make gold nanoparticles all the same. But when you've got this sort of roughly spherical ones on there, they're all identical, they all have this gap. And we can see that it's 0.9 nanometers plus or minus 0.05 nanometers. That's what the statistics gives us. So now I've got this robust construct, I can start doing things with it. And that's what I'm going to show you sort of the rest of today. So I just want to show you that this thing is sort of a bit special. And I'll try and give you the reasons why. So the first thing we have to realize is that no gold nanoparticle is spherical. It's always faceted. No nanoparticle of any sort is spherical. So we have to worry about the facets, and it turns out to be important in this system. So the way that we can look at this part here on the bottom is that really it's just a metal insulator, metal waveguide. So we want to understand what are the modes on that waveguide when this gap is less than a nanometer, or a nanometer, or a couple of nanometers. So actually it's beautiful. All the very, very complicated equations for the modes in that simplify. Most modes are attenuated away and they don't exist. There's one mode that really exists, which is a mode which is in the gap and exponentially decreases in the metal either side. And it has an in-plane wave vector going along here, which is just given by the dielectric constant of the gap and the dielectric constant of the metal. And it's 1 over the gap size. So this can be hundreds of times larger than the free space K0. Okay? So in other words, the effective wavelength in here is extremely small compared to the free space wavelength. It's on order of 10 nanometers, not 800 nanometers. So that's how you can stuff it in there, and it travels along very slowly. Another way to say this is the effective refractive index is of order 100. It's a very slow mode. Okay, so now we know what goes on in the infinite guide. Now we realize that what happens here is that you have these discontinuities at the edges. And these discontinuities mean that you actually have standing waves that sit in here. So they look like Fabry-Perot type cavities. This is a Fabry-Perot cavity, however, that's 20 nanometers long. It's only useful because the wavelength is 10 nanometers. So you can bounce backwards and forwards and get constructive and destructive interference. So in this calculation here, I assume it's circular and they're actually Bessel functions. But it's just the same pretty much as a linear Fabry-Perot. So this is just the zeros of the Bessel functions. And you can solve what are the wavelengths of the modes in there just using a Drude model. So this is just the Drude model here. And that depends on the length of this facet here, so W. So you get a whole set of modes. They're very, very tightly confined in that gap. The volume of the mode looks something like that, RD squared. So it's about what I showed you before. And you can look at the enhanced optical field in that gap, and it goes something like the diameter of the nanoparticle over the gap with some constants in there. So this is why we get very large optical fields as well. And then there's a lateral spread here, which goes as something like the square root of the diameter times the gap size. The problem about this mode here is it's so tightly confined that there's no overlap with free space wavelengths. So even though it would normally exist there, we can get it in many systems, it's normally very hard to couple to. The coupling efficiency is terrible. So there's another set of modes that are really important. And these are antenna modes. They're the sort of things that we started out thinking about, where you actually say have a plus charge here, minus there, plus there, and minus there. So there's a mode that's spread out over the whole construct. And it's closer to the wavelength of light. What happens is these are antenna modes, and if they have the right symmetry, they can couple to these cavity modes. So when they're near resonant with each other, and they all can be tuned to each other, then you get very good coupling to these cavity modes. So that's the sort of trick that allows you to go from free space into this incredibly tightly confined mode. And I'll show you there's another stage of confinement. And it's a bit like impedance matching. So you have a free space impedance, and you can't get down to this completely different impedance for a very tightly confined mode. So you put in matched impedances, and so there's a cascade. And so it becomes better to couple. Now, there are very many reasons this is nice, really good thing to play with. So it's got very, very small mode volumes, but it's very, very robust, as I've tried to show you. It's got these high fields, and it then couples to anything you put in the gap there. So that's going to be interesting for light-matter interactions. The other thing that people find surprising, and certainly has been for us, is that if I put an emitter into that, it can emit light. And to see why that's surprising, we need to go back to something which actually Lucas Novotny showed in 2006, I think was the original theory paper. If you forget about the substrate, if I just take a dipole and I put next to a gold nanoparticle, well, as I put it closer, I start to get more light coming out because the nanoparticle scatters the light out more efficiently. But at some point, about 5 nanometers away, what happens instead is that you excite the electrons in the gold nanoparticle, and then they excite thermal vibrations. You absorb the light instead of emitting it. So it quenches the luminescence like that. So generally people have felt that if you take an emitter and put it within a few nanometers of a metal surface, it's not emitting, it's just being absorbed by the gold. That's not true here because you have a trade-off between different things. This is essentially a waveguide which emits incredibly efficiently, so then it's just a competition in rates. How fast does it get absorbed by the gold compared to how fast it radiates? And in this geometry here, it turns out the radiation wins, so no matter how close you go, you still win. So we get actually now efficiencies, we think, on the order of about 50% emission efficiencies, which is really good for things that we want to do. So I'll show you one of the first things that we did in the system, well, not one of the first things, but one of the first things that really started to show that it was a very useful system. And we're trying to look at taking a single emitter, a dye molecule, say, or it could be a semiconductor quantum dot or a semiconductor emitter, and we want to put it into a cavity. And we want to get to the strong coupling regime. I've worked for many years in strong coupling. It's an interesting system because we mix together the light and matter modes completely. So we have a 2-level system. It has some dephasing rate here, and there's some light matter coupling, so it can emit photons which go around the cavity. They leak out at a rate kappa. So there's a certain cavity Q that we have in the system, which goes as 1 over kappa, right? Now, when this light matter coupling is faster than anything else, then the light the energy in the material mode gets emitted as light, but gets reabsorbed, and then re-emitted and reabsorbed before anything else happens. So you can't say whether the energy is in the matter or in the light. It's cycling backwards and forwards between the two of them. So you get new quasi-particles, which are called polariton modes, which are mixtures of the light and matter. And I'll show you those in a second. But to do that, you need to have, this condition. You need to have this coupling be larger than anything else. And so that sets conditions on the quality factor, because this coupling, as I said, goes as one of the square root of the volume. So if this is the volume of the cavity, and that's the quality factor, I need to be in this domain here to get strong coupling. And these are Purcell factors, which have this is emission rate of the speed up of the emission rate. So I showed you the dielectric cavities before, and this is normalized to that lambda over n cubed, the dielectric volume. So all the ones that we've used before are above this line here. So essentially they have to be in this high Q regime here. The problem is I want to do strong coupling of a single emitter at room temperature, because I'm interested in things like the chemistry I can then do, and it's no good cooling it down to low temperatures. And I also want to get rid of temperature because that's making quantum optics very complicated and expensive. So the problem here is that basically this here is always, this molecule or emitter is always in some thermal equilibrium with a bath. And that has therefore a line width of kT, which means that there's no point in having a quality factor which is small. So I actually have to work in this domain here. And then if I want strong coupling, I have to be in that domain there, which means I need a very small cavity volume, which means I need plasmonics. So that's why for strong coupling of single emitters, I have to have, at room temperature in a way, I have to have plasmonic structures. So that's just the same thing again. Now there's one other thing that I didn't mention yet, and that's that the optical field in the lowest mode, there are a number of different cavity modes here, but the lowest mode for small gaps has an optical field which is vertical. You can see why. The charges are going to build up on either side here, and I can't fit lateral fields in there. So to get strong coupling, I need to make sure the dipole of my emitter is in the same direction as that optical field. So that's not actually easy to do in a thin gap like that, because most emitters want to lie flat, as you'll see. They're organic molecules or TMDs, or everything wants to lie flat. Quantum dots might be better, actually. Quantum dots are one of the only things that might be good here. But there are other problems with those. So what we did was we used the system I've shown you before. We basically used that CB molecule as a scaffolding. It has resonances in the UV. It has no electronic connection here. But we can put a dye molecule inside it in the right orientation. And when we do that, now it's aligned along the field here. So we start off with this plasmon state, which is just tuned by tuning the gap size and the size of the nanoparticle and the contents. And the electronic state, which is here, is a two-level system in our dye molecule. And when we bring them into strong coupling here, we'll get two new states, one higher and one lower in energy. And that's exactly what we see in the system here. So if I look in the dark field scattering, that's the mode that I see. This is when the molecule is in the wrong orientation, and if I put it in the right orientation, I start to see these splittings, which are very, very large at room temperature. So that was a few years ago. It was already a tour de force. We said, oh, we should be able to do all sorts of things like photon blockade. As soon as I put one photon into the system should change its optical response. So it's non-linear at the single photon level. Or what you can also see here is I've changed the energy levels of my molecule. So by mixing light into the molecule, I've changed the energy levels, so there are ideas around that I should be able to change the chemistry. So a number of people here are exploring whether that's possible or not. Or non-linear optics should be interesting. Right, so what I'm going to show you is, so in this system here, we didn't control where the molecule was, which is a major problem. We didn't control exactly how many molecules we had either. We had to count them essentially afterwards. So we want to do better, and to do that, I'm going to go back to what Laura was talking about yesterday, the whole concept of DNA origami. So DNA origami is I mean, it's going to make major impact. It's such a fantastic way of making precise nanostructures. We've used it for about 10 years now, so we can do things like make a single gold nanoparticle next to a single silver nanoparticle and look at their couplings and things like that. But here what we're going to do is use it to make this nanoparticle on Miller geometry. So we make a tile of DNA. It's 2 layers thick of DNA. It's about 30 nanometers across. This is an AFM. They all look the same. I mean, they're fantastic when you do DNA origami, because essentially if you do it right, everything is identical. So this one has some tethers on the top. That's what you're seeing here. Those tethers are exactly designed to pull down a nanoparticle, which we've tagged with another DNA oligomer. So what that does is it creates, as far as we can tell, very precise nanoparticle or mirror structures. They're a little bit thicker than I've shown you so far, about 4.5, 4 nanometers thick. And the nice thing is I can put a single molecule in that structure anywhere I want on the 1 to 2 nanometer precision. And I'm going to show you how we prove that. So what we can do is we can make constructs. So there are various different dye molecules you can tag on to a DNA strand, and you can design that strand to intercalate at a particular place in this DNA origami. So you assemble, a billion of those. And then you do it slightly differently with a different sequence, so it assembles in a slightly different place, and you assemble a billion of those. And each time you make your measurements. So what we did here was we used this molecule, which is a light-emitting molecule. So if we look at one of these constructs, we can now see light emission over time. So there's the luminescence of this molecule, about 670 nanometers. And what you see is it lasts for a time and then it breaks. That's what happens with molecules, unfortunately. They always break. But this is in ambient conditions. So in fact, that's actually a supremely amazing molecule in ambient conditions, how long it lasts. So we can get many, many more photons out of this molecule than we normally can by hiding it in this construct here and essentially sucking out the energy from it as soon as it's excited. So the Purcell factors I'll show you are thousands of times larger than the Purcell factor, that basically the emission of that molecule in free space. So it emits now on the 100 femtosecond time scale. So it basically remains excited for very short times. We can also look at the scattering of this construct at the start. So you see the sort of two modes there. It's not quite strong coupling because they're not quite resolved properly. And then when you've broken the molecule, it collapses. So that's exactly what you'd expect. It looks just like the cavity. And now we can do that for all of our constructs. What we do, in fact, is we look at the light enhancement here, which tells us the Purcell factor, and we do that when we move the dye molecule across the cavity there. So what you can see is you trace out this path here. That is just essentially the optical field in that gap. So what I expect is a mode with a lateral full width half maximum of about 9 nanometers using this very, very simple formula. And what I get in experiment is something about 7 nanometers. So what we learn from this is A, we can place the molecule precisely to about a nanometer. B, we can put the gold nanoparticle on top also to a nanometer. So all of those things have to be precise to be able to get that. We also learn something about the orientation of the molecule. It seems to go in at about 60-ish degrees. It must flex around a bit. We're working on that at the moment. So that's really to show the power. We now can put individual molecules. We can also do lots and lots of other nice things. So Jack is at the moment working on sets of systems where we're putting in more than one molecule. So the first thing I can do, if I put 2 molecules that are identical and near the same place, then what I should find is that the Rabi splitting should scale as the number of molecules square rooted, like the oscillator strength. And indeed, if I look at a whole set of modes, you can see they very nicely, as I increase it, basically follows that formula. So that's really very nice. But I can do lots of other things as well. I can use 2 different molecules that happen to have the same electronic resonance. So I can use light to now couple my 2 molecules together to make new constructs, which are sort of an optical molecule, and so the chemistry of those states should be different as well. So that gets us into interesting domains. We're also interested in what happens to, if I'm exciting 2 molecules and I see a vibration, so I go through Raman scattering, is the vibration in the left molecule or the right molecule, or both of them? And then it gets measured. So in Raman scattering, we've been able to ignore that really until now, but now we need to worry about it. So how coherent is this Raman scattering process here? And I'll show you, we can also now do things like we can just look at a single bond in time and just watch what it's doing. So this is work that's not been published yet, which shows you where we can try and get to. So now we're trying to understand the quantumness of this. If I look at the emission of this molecule, this is a slightly different one, but it's a similar molecule. So this is the absorption line here, and this is the emission line here. So what we're going to do is we're going to excite this. So this is typically how you draw molecules. I think you've seen pictures like this already. I'm going to excite my system here, and I'm going to look at the luminescence here. And I'm going to bring my plasmon into some tuning, but you should note that I can't go into strong coupling on everything at once. I have to decide where my tuning is. I can either decide to put my cavity mode on the emission or on the absorption. But they're in different places for molecules. For a semiconductor, that's not the case. I don't have to worry about this. But for molecules, I do have to worry about it. So what we're going to do here is we're going to do strong coupling on the emission here, but it will not be quite in strong coupling at the absorption. So now what we can do first is we can just try and look at the emission lifetime. So this is lots of molecules in solution. They have a typical lifetime of 2 nanoseconds. Here, all we get is, in the nanoparticle mirror, all we can see is the instrumental response, because it should actually be 100 femtoseconds. But there's no technique that exists at the moment that allows you to look at single molecule correlations, so this is photon counting, on the 100 femtosecond timescale. So we're trying to invent ways we can actually get down to that time scale. But anyway, it looks consistent. Then we can do, now what we're going to do is we're going to pump this transition here. So we're pumping one vibrational energy above there. And what we're going to do is we're going to change, so now we have to use pulses. Because what we want to do is we want to invert the system so we can watch how the light then comes out. Because if we want to get one photon in, we have to exactly invert the system. So we just exactly invert it and get one photon coming out. So what we can do is we can look as a function of the square root of the power. And what that tells us is essentially we're exciting this coherently. So at some particular power, we should bring the system into inversion. But if you excite too much, if you increase the power, it de-excites that two-level system again. So there's this nice geometric picture where you're bringing it into inversion, but you can go over the top and come back. And that's what we seem to be seeing in this. It makes sense. What we now want to do is to sit on that point there and to look at the emission. And when we look at the emission, we see two lines. In fact, the problem is that they change over time because the plasmon resonance is not completely stable. But it looks like it's tuning across the plasmon resonance here. So you see this sort of anti-crossing. And then we can now start taking G2 measurements. We look at the correlation of photons coming out from same pulse versus separate pulses. So the idea of this experiment is for one pulse, I should just get one photon out of this system. I should never be able to get two photons out. So I look at the correlations here, and I can't get two clicks at the same time in this. So that's indeed what we're seeing. When we excite on that first vibrational resonance, we indeed see a G2 which is less than 1. If I'm looking at successive pulses, then I should see something the same. There's an instrumental change here. The areas here are actually the same. So I see a G2 which I can extract, and it's something like 0.5. It is a quantum emitter, which is good. But then there's something strange. As I change the energy of excitation, I actually get to a bunching regime. So it's more likely to emit two photons than not. That we don't understand. We think it's something to do with this molecular nature of the system, but there are no theories yet for this. So I'm encouraging all the theorists to try and understand why this might be going on. You can also play these games looking at things like the TMV systems. The difficulty in the TMV system is that the excitons, if I look at a monolayer system, the excitons are in plane, completely in plane. But I told you my dipole is vertical. And it's very hard to square that. So we actually can get strong coupling. If you look at multilayer systems, then you can see as I tune across it, either I can do it dynamically or I can look at different nanoparticles. I can see this sort of strong coupling. So I just basically have my, this is tungsten diselenide, I put it on gold, and I put nanoparticles on top, and I look at the modes here, and I can see these modes. So indeed here, the nice thing is I can actually see in luminescence also the two modes. So there's one mode there, another mode there, and that's the strong coupling. But that's for 12 layers thick. So why do I need 12 layers? Well, it's because in a monolayer we have this problem here. So what happens is I have more layers in the TMD, then I have the exciton actually delocalizes more three-dimensionally. I can't stack those layers. They actually have to be properly in electronic contact. So these are exfoliated samples. They're okay. So what you can do is look as a function of the number of layers, and you find that after about 4 or 5 layers, you start to see the strong coupling because the exciton now has enough dipole which is vertical. There are other cavity modes that you might have thought would work, but the problem is that they tune off resonance into the infrared. For these modes here, when you make the gap smaller, the modes tune right into the infrared. So it's very hard to stop that. And the other problem is that each mode has both, if you like, a positive and a negative part of the mode. But the coherence area of the exciton, the coherence size of the exciton, is larger than that. So what you're doing is basically that says it's the wrong symmetry to excite excitons. So there are lots of interesting things that we're going to have to sort out to get this to work. But it should be promising because the excitons are all confined in a very, very small region, so they should see each other. So interactions should be very strong in this system. And we do see nonlinearities, but we don't yet understand them. Right, okay, what I want to do is, how are we doing for time? What I want to do is to now talk about some of the new behaviors that we've seen which tell us that we can actually confine light tighter, and tighter than I've shown you so far. And to do that, we have to actually understand an experiment that is scaled down by a factor of 13 orders of magnitude. So actually, the original experiment is based on the gravitational wave detectors, which is basically just a big interferometer with very big laser beams. And the reason that's interesting is because it actually has a vibrational mode. The mirrors in a gravitational wave interferometer are huge, and they're hung from glass fibers because you want to have them out of contact with the ground. You don't want any vibrations to come into them. So essentially, it's on a little pendulum. So it's got a vibrational mode. And the light intensity is so strong that when it's reflected, it kicks the mirror. And so there's a coupling between the vibration and the light intensity in the cavity. So that coupling is called optomechanical coupling. So if I just look at the modes in the system, that's the photon there, this is the vibration. So now people make microfabricated versions of this, and it looks just like that. So your Hamiltonian has a coupling which is dependent on the intensity of light in the cavity and exciting the phonon mode, and the coupling coefficient is often called G. And this G, this coupling coefficient, goes as something like 1 over the optical volume. So the energy is unbelievably small in this case, and even in the microfabricated cases here, it's still on the order of nano-electron volts. And so people have made all sorts of different systems I've drawn here which look at that coupling, but the reason that they actually have to cool them to millikelvin is because of that energy scale there. The interesting thing is that this system here, in fact, coupling of phonons in a cavity, the molecular phonons, is the same system. It has the same Hamiltonian. This is the Hamiltonian for Raman scattering. And so now if you calculate that G in the system, it's on the order of milli-electron volts. So it becomes accessible in the experiments that we're going to do. So now what we can do is we can look at what the Raman scattering process is. So here in my lowest vibrational level, what I can do is I excite with a laser to a virtual state, and it drops back down to this vibrational state, emitting a photon which is red shifted. So if I put in a laser here, then I expect on the longer wavelength side, the lower energy side, to see the vibrations of my molecule. But I can also run this in reverse. So I can go up to this state from the first vibrational state and then down to the ground state. So that will be blue shifted, and I would see these photons there. And the ratio of those basically tells me the occupation of that first level there. So if I look at some temperature and I look at the ratio, well, basically it's a thermometer. I can measure the temperature by just looking at the Stokes and the anti-Stokes scattering. So what we started to do was to do experiments where we cooled the system down to 10 Kelvin, so there was 0 occupation there. So this energy difference here is 100 milli-electron volts. So, you know, that's 0.5 milli-electron volts. So there's no occupation there. So indeed, you don't see any anti-Stokes scattering, you just see the Stokes scattering. I'm just working in a regime here. Now I'm actually looking at maybe 50 molecules in the gap. They're electronically non-resonant, completely in a different place. So I'm just looking at the vibrations of the molecule. And then sometimes what I see is something like that. So what I see is very large anti-Stokes scattering. And if I look at the ratio here, then the temperatures I get is like thousands of degrees. So the system cannot be thermalized because gold melts well before that. So what's going on in the system here? You can see that the lines are sort of new here. They're not the same lines as here. And they move around a bit, the same on both lines here. So I'll show you how we can analyze that. Essentially, this is this optomechanical coupling here. This G, depending on how G is, it gives us a measure of the volume of the mode. So because we have this link here, so I can actually, from these experiments, extract a volume. And we find the volume is really small, less than a nanometer cubed. So something has happened in the system that dropped the volume. And what happened? So what we think happens is we start off with the facets in the gap. This gap is maybe 1.1 nanometers. And what happens is we pull a single gold atom from the facet and we pull it down towards the gap, but it's still in contact. This is a classical calculation of what the optical field then looks like, but what you find is that it's actually enhanced by a factor of 4 or 5 just on that tip there. And if you rigorously calculate the mode volume there, then you get less than a nanometer cubed. So how do we do those experiments? Well, what we do is, as soon as we see this forming, what we start to do is to change the optical power. It's stable for quite a long time. So what we can do is a power dependence here. We can do it actually many times. So that's a power dependence on a single, what we think is a single molecule, which is sitting underneath here. And from the gradient here, so basically we extract the occupation of that vibrational state, it tells us the G directly. And from the G, we can get down to the cavity volume here. This is the Raman cross-section, which we pretty much know. We know everything else in the system. So basically, we do this a number of times, and we can measure this coupling coefficient, which tells us that the volume's really always very, very small. So does this make sense? So the first thing to realize is that this process here seems to depend very strongly on the light intensity, is exponentially dependent on the light. And if we actually turn that into an energy, we find we get an energy on the order of about 0.8 eV. That's about the energy of an adatom on gold. So it makes sense that's the energy to pull a gold atom out. What we find is that if we turn down the optical power, it will stay there for as long as we want. And then if we increase the power, it'll suddenly pop back. We don't understand at the moment what the forces are, what the mechanisms are. So people have tried on UHV SDM to understand gold atoms moving around. We also know that the classical calculations are pretty much backed up by a quantum calculation. So that's another whole aspect which is interesting here. So this is Martino Beata in San Sebastian. So how is it that we're able to get away with using classical calculations for the field at the single atom scale? And it's really because the electrons just move into a single atom and out. The electrons remain delocalized. And it's basically a lightning rod effect for but down at the single atom scale. Okay, so let me just go a little bit forward. So I just want to show you what happens. So those experiments were CW experiments. But you can do those experiments with pulses now. So I want to know what happens if I increase that occupation even further. So this is the theory actually done for CW as to what you'd expect. So what I showed you before was that this is the number of photons in the cavity as I increase the laser power. So of course it's just linear with the laser power here. But if I look at the occupation of the phonons, well, to start with at low power I just see the thermal occupation. But as I increase the power more, what I start to see is I'm pumping that system. And so I showed you this range here, but I want to get to this range here because something strange happens. If I look at the coupling in the system, the damping starts out finite but actually goes to 0 at a particular threshold. Essentially what happens is the vibrating thing starts oscillating spontaneously if I pump it. And it depends what color of light I'm using to pump the system. So people have done that in the microfabricated system. The question is, can we do it with molecules? So we're looking for this signal there. So what we do, we now actually, to get to the vibrational densities, we need to increase the power, so we use pulses instead. And what we see at the very highest powers is we see something which is distinctively nonlinear. It's superlinear. So that seems to actually work. It's at the right position for the thresholds. We can again measure the coupling coefficients, but then afterwards the molecules break, sadly. So before it goes into the spontaneous oscillation, it looks like molecules don't like to do that. And what they actually do, we actually seem to be going up this vibrational ladder here. We're starting to populate higher up. And then the molecules can go over to a different energy scale here where a bond is breaking. We don't understand the dynamics of that process or really the energetics of it yet. But we can do, if you like, we can engineer our vibrational system by chemistry because we can make different molecules. So that's a lot of what we're trying to do now, is to treat molecules as of engineering things. So I mean, just to show you it's a strong effect. So that's the background, which is completely linear, and this is the non-linear Stokes emission that you get out. It's very strong. So I'll very briefly just show the sort of places that we're going. It turns out we can actually get all of this working at room temperature now. All that happens at room temperature is the dynamics is faster. So you've got to be better at taking the signals. But you can see it here. We're just looking at the Stokes side. You suddenly see very strong lines. They move around, so it has to be a single molecule. And you can actually watch a single atom appear and disappear. So we're still trying to understand how light can pull out those single atoms. What's it doing there? We can also design molecules which have a particular signature bond which is close to either the nanoparticle or the mirror on the bottom. So we can try and understand, where does the atom come from the top or from the bottom? And we can also use this triple bond as a marker. We can actually watch a single bond in real time. So that's the sort of directions that we're going on to now. So what we don't understand at the moment, but we're getting somewhere, is it does not look like the movement of the atom is independent of the movement of the molecule. Because the molecule has to flex. There's actually no space in there. I draw it in this very easy framework. It doesn't look like that at all. So there's some cooperative interaction between the metallic atoms and the molecules in these systems. So we're really, I mean, this is really what I wanted to do at the start. And we're actually looking at things on the nanoscale now. So with this, we're actually doing things that you cannot do with electron microscopy. But it's all in ambient conditions, so you can actually do the chemistry in a realistic way. So we're trying to look at, say, chemical reactions of these. How do electrons come through this system? So I'm happy to talk more about that. We've got lots of experiments, but what I'll do is just, I'll finish up now. I'll show you 3 sort of directions that we're trying to go in. One of them is we've used the electrons created by the plasmons in the gap to do free radical polymerization. So we can actually coat nanoparticles in various different ways just by controlling with the light. We can also look at electrochemistry. I can use this as an electrode and I can watch the molecules at the bottom changing as I put potentials on here. We can use molecules as springs, and we can use them as sort of quantum springs. So we're trying to understand that. And we're trying to understand this single atom chemistry. So I hope you're convinced that this is a very, it's just nanoscience. People always ask me, am I doing chemistry or am I doing physics or material science? And this is really where nanoscience is. I'm a complete advocate. It doesn't make any sense to ask which discipline it is. It's all what is going on, what are water molecules doing in this system here? There are ions around as well. We're still trying to understand incredibly simple things like what's the refractive index of DNA origami, right? Which looks like it's above 2 in various ways we've measured, but it can't. People say it can't possibly be, but you don't understand anything. So it's a very big collaborative team, people from different disciplines. Everybody has to produce a cake when they produce a paper. We have lots of cakes. They have to be in the style of the paper. I did one last Monday as well. Yes, so what I want to give you at the end is that why I think this is such an interesting area at the moment is not just that you can look on the nanoscale, but it opens up these ideas, things like Laura were talking about, of making nanomachinery. Because nanomachinery in the end is going to have to be controlled by light. You are not going to make electrical wires connecting to every little nanomachine you have. So we have to find ways to make nanomachines move around. I didn't have time to talk about that. But we also have propulsion systems now which are light activated, where we can move objects around. So anyway, I hope that gives you a vision. I'm very happy to talk to you more throughout the conference. Thank you.